I want to continue our discussion of chapter 18 and the ray model of light with a topic that's very interesting called total internal reflection. And so total internal reflection is a phenomenon that happens when light is passing from a material with a higher index of refraction into a material with a lower index of refraction. And to show you what I'm talking about, I have here this jar and it's full of water, and what I've done is dropped a few drops of milk in there to give the light something to scatter off of. So hopefully we should be able to see a nice beam as it passes through there, and indeed we do. Notice what happens as I make the beam interact with the top surface. It bounces right off. It doesn't pass out of the water and into the air. It bounces right off. Notice that that does not happen coming in this direction. Ooh, but it is happening off the side of my glass. So that's pretty cool. Again, total internal reflection only happens when light is moving from a higher index of refraction to a lower index of refraction. We don't see it when the beam is moving this way. We do see it when the beam is moving this way. Here I have water with some drops of milk in it and oil on top. Let's see. Oh, that's kind of interesting. We get a little bit of bending action. No internal reflection, no total reflection yet. Oh, and we can see here that we get a bending towards the normal in the oil and then back away from the normal in the water. That's pretty cool. When we go this way, what do we see? We do not see total internal reflection off of the boundary between the water and the oil. We do see it between the boundary, or at the boundary between the oil and the air. Why? Because oil has a higher index of refraction than water does. So we will never see it at this boundary between the oil and the water. We will see it at the boundary between the oil. We might be able to observe it at the boundary between the oil and the water if we come in from the top. Let me see if I can do that. And indeed we do. Look at that. That is pretty cool. We're seeing some reflection off of the boundary between the oil and the water. Again, we don't see it here. Why not? Because the oil has a higher index of refraction than the water does. Pretty cool. Okay, so total internal reflection occurs when a light ray is unable to refract through a boundary, and instead 100% of the light reflects from the boundary. So this is a nice picture of the phenomena I was just trying to demonstrate here. Notice that if the angle of incidence is 0 degrees, we see no bending of light at all. And that's generally true, no matter what direction we're going. As the angle of incidence increases, however, we start to see more and more bending. And at some point, this refracted ray would have to bend right along the surface of the water. In essence, the refracted angle would become 90 degrees, but that's not even leaving the water. So it's not leaving the water, it's not refraction, it just reflects. And that's what we see here. This light ray bounces completely back. Here's a nice schematic of the same thing. No refraction for an angle of incidence of 0. Increased refraction for increased angles of incidence, and we also start to see this reflected ray increase. Once we reach the critical angle occurs when that refracted ray would get refracted at 90 degrees. So when the angle of refraction is 90 degrees, well, that's the very most that anything could be refracted, and that's right along the surface of the water. That's not refraction at all. At that point, it switches from refraction to reflection. And at any angles greater than that, we continue to see reflection without any refraction. And so this just comes out of Snell's law. Notice we get the theta critical here when we plug in 90 degrees for the other angle. Sine of 90 is 1, and so we end up with theta critical equals the inverse sine of n2 over n1. It can sometimes be a little bit tricky to remember which is n1 and which is n2. But remember that this only happens when we go from a high n to a low n. So n2 always has to be smaller than n1. If you forget, it's really no big deal. because your calculator will yell at you. It won't let you calculate this if you get your ends backwards, because it cannot take a sign of a number greater than 1. So if you are trying to calculate a critical angle and your calculator is yelling at you and being like, I can't do that, then you probably just got your fraction upside down. You probably switched your N1 and your N2. This actually has a lot of practical applications. It turns out that, a fancy camera is a mirrorless camera. What does that mean? Well, you can actually achieve greater pass-through of light using total internal reflection than you can using mirrors. Even the best mirrors have some reflection off of the front surface and not perfect reflection off of the back surface. It turns out that using prisms to redirect the light, using total internal reflection, is just a more efficient way of doing it. You end up getting better optics doing it this way. Here's an example. A light bulb is set in the bottom of a 3-meter deep swimming pool. What is the diameter of the circle inside which a duck swimming on the surface could see the bulb? Okay. Well, why don't you give this problem a shot? And if you get stuck, check back in with us. Or if you don't get stuck, check back in to see if you got it right. Okay, so this is our basic setup. We've got the light bulb here. The light is, of course, coming off in all directions. Of the infinite number of rays coming off of this light bulb, I've drawn 2 here. Why did I draw these 2? Well, because this is the critical angle. And so notice that if my duck is sitting right here, here's my duck. If my duck is sitting right there, he cannot see the light bulb. Why can he not see the light bulb? Because any light that might be headed to his eyeball hits the surface and is reflected. Because of total internal reflection, it's reflected away. However, if my duck was sitting right here, he is a happy duck. Why? Because he can see the light bulb. Any light heading in his direction here will make it out of the water and into his eye. Out of the water and into his eye. See how happy he is? He can see the light. Okay, so in order to figure this out, the first thing we need to do is to figure out what the critical angle is. So, here we go. Theta critical equals the sine inverse of N2 over N1. Now, which is which? Well, we've got water and air. In order for our calculator to not yell at us, we just have to put the small one on top. And it tells us that the index of refraction of water is 1.33. And so we run our calculator, and we get 48.7 degrees. Okay, now we're basically done with physics, and we need to do some trigonometry. We know that that is 48.7 degrees. We want a diameter, and so let's go ahead and make ourselves a triangle here. And I suppose I will make my triangle over here. There is my triangle. Again, this is theta critical. This side of my triangle is 3 meters. This side is the radius of the circle that this duck can be in, aka the diameter divided by 2. And so I'm almost done now. I can just set up a trigonometry problem. We have opposite and adjacent, so I can write that the tangent of theta critical. So tangent of theta critical is opposite over adjacent. Opposite is d over 2. Adjacent is 3 meters. So this is over 3 meters. Now we can plug in all of our numbers and roll with it. So we should get what? D is equal to 6 meters times the tangent of 48.7 degrees. And we get D equals 6.8 meters. Okay.